Okay, hi everyone. My name is Samantha Pelayo Cazares. I'm a master's student at the University of Toronto in the Department of Civil and Mineral Engineering, and I'm supervised by Dr. Jennifer Drake. As she mentioned, I'm going to be talking about the customized flow sensor that we developed to measure the hydrological response of some beds at the Great Roof, the second actually Great Roof located at the University of Toronto. So here's a little bit of a picture of what the actual field work looks like. So it's very nice and I feel very lucky to be working there. So just to give you a little bit of background, the Great Lab 2 stands for the Great Roof Innovation Testing Laboratory. This is actually the second location, and this one's located at 1 Spadina Crescent, just downtown Toronto, on campus. So a few of my colleagues have previously talked about it. It's also important to note, I think, that it just started research operations in fall 2019. So, and then we got hit by COVID. So there's a little bit of a gap in there. And it's approximately 155 square meters of testing area with sedums and native species, as well as biochar and controlled test beds. Also, we have 4 test beds that are just completely, impervious. They were 4, now we have 2 of those, and there are several studies going on in there. So as you can see here in the picture, just to show you, this is where the testing area is. That's kind of active right now. And I'm just measuring 8 beds, and each bed is approximately over 3 square meters in size. So basically, I'm going to be talking about the challenges and the objectives of this research. I'm going to start with the challenges because I think it's important to address this and why this is important. So for example, the roof or the Great Roof Lab where we are located is actually on a very historical building. Therefore, everything has to be quite low in height just to protect the view from the street. So that's why we have a limited space to place the equipment. So let's say a tip and bucket rain gauge. Probably some of you are aware of that, but it's quite high. And then the challenge we had here was that in average, we only had 15 centimeters of space between the pipe that's actually discharging the runoff on each individual plot to the ground, basically. And also one of the challenges was to measure the runoff discharge as close as possible to the source with cost-effective equipment. So I decided to get the little piece we have inside the container shown here, which is a tip-in bucket, but it's just the individual part. And what we did was actually customize it in order to protect it as if it was a rain gauge. We have kind of the core, and just we were really interested in measuring the rainfall or the discharge caused by rainfall. And then we had some kind of just directing the flow into it with just ABS pipe fittings and parts. So as I said, the general objective was to measure what the beds were discharging, and the objective of this particular calibration work was to characterize the flow measurements errors introduced by either increasing the flow rates, because the Great Roof will not discharge at a steady flow rate, and that will be caused by the fluctuation in the rainfall intensities that we observe, as well as the distance between the end of the funnel. It's kind of hard to see here, but this is the end of the funnel, and the tip and bucket, what I said, is the top of it. So basically the distance between, or the distance of where the water is being impacted on the tip and bucket surface. And this is because the roof has a slope, the roof has a slope, And so we wanted to kind of like characterize under what distances we would have better or a worse performance of the readings in like the tipping bucket. And just to make sure that we were measuring accurately what was happening on the rooftop or what's actually happening. So the monitoring equipment basically consists of like the technical equipment consists in a Davis tipping bucket single spoon, which is this one. And then that one has to be connected to a pulse input adapter in order to make the signal from this device be compatible with the Hobo microstation, which is the data logger. So luckily we had like 5 actually ports, or like 5 measuring devices can be put into one. So that's very cost effective because we don't have to buy one for each single device. And I'm just going to show you a quick little video of me assembling the measuring device, because all of this was actually done like manually. We had to put things into place, make sure that they were like secured, fixed into the actual place. We created then the connection with the wires. We needed to strip them and like create the connection manually. And we did that for all of our sensors. Then we would put them like into place, like where the discharge will be. And then we would actually just test them to make sure the signal was successful and that the data logger was actually logging the tips recorded by this device. So it worked all good. And now I'm going to move on to the calibration part, which is, this is the setup. It was actually done in 2 parts. So we had one experiment for steady flow rates, which consisted in 9 different flow rates, and they were run for 30 minutes each. And we also did this for like the 3 distances, D, which would be the distance between the end of a funnel and the top of a tipping bucket to like this value is presented on the screen. And we also ran this for like triplicates, so like 3 times just to have an average. And yeah. And then the second part was an unsteady flow rate experiment, which consisted in simulating 5 rainfall events representing the Toronto summer climate. And then with this, with this calibration part, we wanted to make sure that we were understanding the behavior of a tipping bucket. So this is the device. It was under controlled situations or conditions, which was like the flow was fed by a pump that was calibrated before placing the tubing into the fitting parts. And then you can't see in the picture, but we had the same setting with the microstation, data logger, the impulse adapter connected, and then they were being downloaded after each experiment to have the results. So moving to the results for the first experiment, which was under steady flow conditions, this was the level of error that we found by our device. And you can see the different scales, or like, yeah, the different scale of error according to each applied flow. We chose 9 flows because it was like a wide and variety of like flows. We also found under this experiment that the limit of, or like the limit, yeah, like the capacity of the tipping bucket was about 342 milliliters per minute, which would be equal to 60 tips per minute. So 1 each second. And this was found, yeah, like, so basically the behavior is that if it tips more than 60 minutes, theoretically it's just like going up and down, and not all the water is being collected in the bucket. So with this experiment, we also decided that what we would place on site was going to be the distance between the end of the funnel and the tipping bucket was going to be 1 centimeter, because it technically behaved a little bit better among all these flows. Moving to the next slide, we had the unsteady flow conditions, and this one is just a residual plot of like the level of error that we observed in other flow rates. All of them were below the 342 milliliters per minute. And I think I'm just running out of time, so I'll move forward because that one is a little bit more clear. So we overall found kind of like a better behavior of the tipping bucket under high flows and not so well behavior over medium to low flows. This represents overestimation of the flows, which means the tipping bucket was tipping or making more tips than it should. And this one was kind of catching up with the actual flow rate being applied. And then more water was being lost due to like that inertia movement. So we decided to categorize the error or like the readings into 3 categories. So the very low one will not need correction for the data observed on site. This will be the equation to correct the flows or the observations found in this category. And this other equation will be the ones for this other category. So just to summarize conclusions, it's important to understand the behavior of the flow sensor. We saw overestimation happening for applied flows between 23 and 200 milliliters per minute. And on the other side, we found underestimation of the applied flows between 200 and 342. So we'll use this data to correct the one observed on site. I just want to briefly acknowledge the funding from NSERC, MITEX, my supervisor, Professor Jennifer Drake, as well as the support from the Drake Research Group and the DesignLIFES group. And that's all. Thank you very much.